My name is Pat Goodson. I've been a longtime member of TGWA and periodically been pressed into service like this, and happy to do it. I did want to make one comment about Scott's uh, presentation there, because years ago in the mid 80s, we did some environmental drilling in El Paso. And as part of that, we were drilling mud rotary, and we had to get a meter, or a hydrant meter from the city, and they came out to the job site, which was at a roadway facility. And so we met them out there, and they put the meter on the hydrant, and we're all kind of standing around there, gave them the check or paid them however we were going to do it. And they said, "So here's the deal, boys. Y'all are from Austin. Y'all don't really understand about the way we do things in El Paso. We're going to tell you one thing: if we come out here and there's water running down the street from that meter or from your water truck, somebody from here is going to jail." So that was the end of that for me. That we didn't. They were serious about that. That was probably 1986. So that was they ran their business very well. Today's topic, this drilling adventures in far west Texas, is just it's going to be a few description slides and then a little project story about how it can go. Challenges that we as drillers or geologists or landowners come up to is one thing is to really understand the geology. And in far west Texas, you don't have to move very far to be out of what you're accustomed to. And whether you're going mud rotary or air rotary, or you're going to go shallow or you're going to go deep, or how it's going to turn out, it's all a function of the geology. Out here, there's also a very real possibility of not finding any water at all. And drilling a dry hole, the word gets around. It's not a great calling card. Then the next thing, obviously, is finding water of suitable quality, whether it's for public supply or ranch water or residential. Obviously, it kind of goes back. We have this friend of ours, Joe Vickers, that says that bad breath is worse than no breath at all. So it's sometimes you just have to take what you get and treat it or not. Locations out here can be, because of the topography, sometimes it's very easy. Sometimes you just drive right up to the locations. Sometimes it's a real challenge, and they have to build roads for you, and it's just not something that can be taken for granted and just assume that it's going to be an easy operation. All the easy sites have already been drilled, so you're coming in later. Power supply out here, anybody who's worked out here to any extent knows that can be it's very expensive. A lot of the grid out here was put in during REA, and they literally would build a mile of power line out to one well. Back in the old days, now they charge you by the pole, and it's very expensive. So another consideration, solar can help with that, but solar, as you know, has limitations as to the depth and volume and daytime pumping. And then again, those of us that have been out here and done a lot of work out here, know that moving people around, where are you going to stay, and get from the motel to the job site and then work today and then get back to the motel or whatever, man camp, or however you're going to arrange it for materials to be hauled out there, where you're going to get water. All of those logistical things are enhanced here so much more than they are, working, for instance, in the city or in the suburbs. This is one of the things we've always been looking for. All of us is out here. Anything they're going to do, they're going to have water, whether it's ranching or residential or whatever. They're going to have water, and many times it's not thought of on the front end. A lot of times they get pretty far down the road on their project before they start thinking about, where am I going to get the water to do whatever it is I'm trying to do. This is an old TxDOT photo. Out here, there's even guys that well service people that have helicopters just because of the distance to get to the wells. They can take a control box and a multimeter and go out and diagnose to figure out if it just needs the reset button or if you're going to have to come out of the hole. So this is a guy over near Dryden. As Scott was talking about too in El Paso, all these little towns out here had a really started out fairly simple on the water. Sanderson was a railroad town. And in the beginning, there was a fellow named Wilson that went in. They tried multiple locations out there, and they drilled a bunch of dry holes. And he finally hit right there in town on the edge of Javelina Hill. So they put the whole water system right there. You can tell multiple wells close together. But before that, they were literally hauling water in barrels to people's houses, sort of like he was talking about in El Paso. Another good source, as most of you know, this being the geo class, is that many times the GAT or understanding the surface geology, you can make determinations about where you're going to start. You can look for structure, which is always in fractured bedrock is an advantage, and so investigating this on the front end can really save you a lot of time. It can help guide where you're going to try to locate the well. Out here, another thing, the way that West Texas is different is that you have all different kinds of water bearing zones within a fairly small area. So if you're based in Alpine, or you're based in Sanderson, or you're based in Terlingua, whatever, you can get the wells can be in any of these water bearing zones. So we talked a lot today about the carbonate aquifers and the volcanics, the alluvial aquifers and the bolsons. Those are you're going to have different drilling methods for each of those, with ranging from some of those alluvial wells or things down along the river. I mean, you could be cable tool. Some of these other projects can be air rotary. A lot of them are going to be hammer. And so understanding what it's going to take, what type of equipment it's going to take to drill the hole, also what the hole diameters are. Again, if it's a public supply well, it's going to take, you start trying to drill a large diameter hole in some of this alluvium or these bolsons, it can be an adventure. Once again, a lot of you guys are very experienced in doing the groundwork ahead of time. Water Development Board groundwater reports. Rusty and I were talking earlier about a lot of this work was done back in the 40s and 50s, and they generated a lot of really good reports, well records, and they things like depth and material they encountered and water levels. That information was really good, and those reports were really good. So accessing those, looking on the Water Development Board water well database, I think everybody that's in the business here knows about going and researching that. The information is sometimes it's very good and sometimes it's not, but it's at least it's a start on trying to figure out what you're going to get into. Going out to these ranches and talking to them, looking at their owner records, and they range from everything. Some of them have wells that were drilled back in the 50s and 60s. They'll still have the original receipt showing depth, materials that were placed, records of pumps they've pulled, equipment that's been replaced, wells they've plugged. All that information is available. Some have absolutely nothing. So if they've changed ownership and things like that, a lot of times that doesn't convey. And then just going out and looking around, and you go out to these wells and you'll see the evolution where it started out as a windmill, and you see where they cut the tower down and moved it out of the way, and then they drug in the pump jack. In the case of some of those really deep wells, you'll see the footings for the pump jack that's there. Then you'll see a stack of submersible pumps and motors laying there on the ground. And you can get an idea. You can look at the fluid ends that are laying there and get an idea. Look at the motors for the horsepower. You can glean a lot of information. we call it the Christmas tree when you go out there and see the stack of motors and they've got them stacked up and it's like a triangle from a heartache through the years. Then you can, and collecting information, also measuring water levels. That's always a good thing. Obviously, we like measuring water levels on open holes with no pumps in or equipment in the hole. You also can figure out, again, if it's, sometimes you can determine if it has junk in the hole, if you can't get down, if there's you just put all this information together to come up with what has gone on previously out there. Another good thing when you're drilling is to go out and collect samples, and good ones, not just a pile of mud that all the samples look exactly the same. So that, when we get done drilling, we can actually assess the samples, make determinations about how you're going to complete the well, not just relying on our memory. And when you have a geologist or engineer that's coming out to the site, they really like to see a nice set of samples, be able to tell where you are and what you've been through. Going back to that, finding like a detective, right? Finding information at the site. A lot of times you can go, this is a windmill footing, you can see, and they wrote the date, and then they'll put the information on the horse trough. Sometimes they have the trough there, they'll write the dates on there, and sometimes depths. One of the places that I really like to find them is on the windmill legs. They'll write it in pencil. It'll last 40 years. You can see how many joints, how many sucker rods or joints or pipe, or what the water level was, and can be a lot of good information that you just have to look and you can find it. It's not always there. In fact, most of the time it's not there, but sometimes you're lucky and you find something. And of course, as always in this business, it's talking to people. Talk to the guy that's been operating. A lot of these ranchers out here, they lease these places, and so they came in. A lot of the water system was already built and had been operated for 40 years before they got involved, and they know what they did, but they know which wells are operational, problems they've had with them, and kind of what to expect in a certain area. Sometimes they don't know anything, but always nice to visit with them. Then you call Joe Vickers, right? Call Joe and say, hey, what do you think? We're going to do this is where we're going to work and what we're going to do. And he's always a wealth of information. This is a fellow over in Central Texas that has done a lot of work all over the state and wealth of knowledge. Now I want to talk about a project that I got involved in years ago. Down in South County, South Brewster County, they put together the Studi Butte Water Supply Corporation, and because they had no centralized water system down there, they had one. I guess there was one old well there near the Starlight that supplied basically the whole ghost town, and people hauled water in barrels, and it was just had been doing it for a long time, and the population was growing, and the businesses wanted to grow. So they got a loan or a grant, I don't know which one it was, from USDA to drill a new supply well. So that was in '98, and we got the contract to go down there. And again, there was not a whole lot of, there was a lot of good geology information because everybody likes to go down there and look at the geology, but there weren't a lot of records about wells and kind of what to expect. So wasn't a wildcat because people did know some things, but nobody had drilled a well there and hit and made a public supply well, and they didn't know about anything about volume. So again, they got a grant to drill the new well, to build an RO plant, and build a couple of storage tanks. The way that, and we were, several people, Kevin included, have talked about the stratigraphy down there at the surface where we drilled it. We started in the Boquillas. Now, I don't know if it was which member of the Boquillas it was, but started in the Boquillas, went down. This is what we anticipate, go through Buda. Normally, you can tell when you're going through the Del Rio, it's fairly, the material is significantly different than the Buda. And then we were going to complete in the Santa Elena. And so that's the section. So, and they bought a piece of property behind the Starlight, and that's where they were going to build everything. And so everything had to fit right there on this really kind of a small piece of property, and they had no power there when it started. But from that spot, it's kind of up on a hill, and you could see the whole area out there. And I think this next picture is actually, so that's a picture of the not a very good picture of the location, but you can see you're looking back to the east. You see the parking. You see mule ears over there. I forgot to run this thing. There's mule ears right there. That's Castellon. And then over to the right, you could see Reed Mesa, and you could see the mouth of Santa Elena Canyon. Well, we're starting in the Boquillas here, right? So there's something going on structurally. And so there's the Tolima Fault. And so we were looking across, and you could see the mouth of that. And that was going to be what turned out to be about 800 feet below where the rig was set up. So we drilled a 6-inch or 6 1/4 hole to 1160, which was, I think, the contract thing. Well, we hit water about 900. We never circulated very well. It was fairly weak on returns. We didn't have any trouble making connections or any problems like that, so we weren't afraid of getting stuck. So we kept going. Again, we went through the Boquillas, Buda, Del Rio, and we hit the Santa Elena about 780. And we went on down to 1160. We logged it, and sent it to the engineer. And we came back, and we decided we were going to set surface casing to 850. And again, we didn't hammer any of this. And some of that stuff, Buda and the Santa Elena, are really hard. It took a long time. So we started out, and we made another probably poor decision. We decided we were going to do an intermediate pass on the reaming and then come back and do a final. Well, when it's misery, it's not something you really want to do 2 or 3 times, but we did it anyway. And so we started reaming. We drilled it with a 9 7/8, and then we came back with a 14 3/4, and then we ran that 10-inch in there and cemented that. Of course, that all that fractured bedrock down there's no returns. And so top off was an adventure. We put a lot of cement as top off on the backside of the casing. After the cement cured, we drilled out with a 9. So it was 10-inch. We drilled out with a 9 7/8, and we went on down to 1160. And again, we had not a whole lot of returns, and so we didn't really even know how much water it was making. We were running enough back pressure on the system we knew we had water in the hole. We just didn't know how much, or if it was going to meet the capacity that they wanted for the system, which was, I think, 150 gallons a minute. So after all that, after setting the casing, cement that, TD the well and everything, when we put the test pump in there, we didn't know what it was going to make, which is common out there. That's not unusual. So there's state Texas well report, state well number. So the pumping test, we had to do the 36-hour because it's a public supply well, and they wanted to pump it at twice the design rate. So we went ahead and we bought the test pump to make the 250 gallons a minute. We set the test pump. I think it was pretty sure it was on 5-inch. Drop, set that. And set it just inside the casing. And we started the pumping test, and it turned out to be a good well. We had about 11, 12 feet of drawdown after 36 hours. And we found the water temperature at about 110, and which that really became the biggest problem that we had to encounter was that water temperature and the crappy quality. It was really, I think it was like 2,500 TDS water. And but again, right? Bad breath better than, no breath at all. And so we started coming up with our permanent pumping equipment design. We had taken into consideration that it was hot water is fairly deep. They wanted to use the permanent pump. At least initially, they were going to drive the RO unit with the well pump, which meant we had a lot of excess pressure at the surface. So we ended up, it was a 100 horsepower motor we had on the test pump. So we ended up just derating the motor for the permanent pump. We just put the 100 horse motor on a smaller capacity, 125 or 125 gallon minute pump, and that worked good. In fact, there's more to the story now to tell you, but it turned out to be that actually was probably, instead of a bunch of wild high temp motors and things like that, just an oversized derated motor shrouded was probably a better install. And in that time frame, the variable frequency drive was just barely coming into being used on submersible pumps, and the power company required that we had a soft start because if we tried to load that motor on that line, it was going to create a problem with Rio Grande Electric. So we get all this stuff, we get all this equipment, and we take it out there, the soft start and the pump motor. We pull the test pump out, put the permanent pump in there, and we start trying to operate this thing. And we had the soft start had protection on it. And this is, you pump installers, you know what I'm talking about. The big problem down there is unbalanced power. So when it's running, the amperage pull on each of the three legs of the three phase is not equal or even close. And consequently, the protection on the soft start would never let the pump run, right? It started and run like 30 seconds and then it would shut it off. So we get the power company down there, and the power company comes and they look around and adjust the taps on the transformer, and they do all this. We're trying to help you. We're going to get this thing resolved. And as soon as they couldn't get it resolved, then what they tried to do is to figure out how it was something we did, right? There's something wrong with our pump and motor. And, if we got they take a set of, like an ohmmeter or a megometer or whatever, and they say, oh, we detect a leak down hole. And just, once again, just trying to kind of to put you off. And so they had to put a generator down there. Of course, we ran fine on a generator, and we never had a problem. We didn't have a leak down the hole, never tripped anything. But just to get going, they had a generator for a while. And we used the soft start, which we didn't need for the generator. But anyway, so again, it was faulting out for current imbalance, and the system wouldn't work. So the system had a guy that was the president of the water board, was a guy named Dave Fricker. And I don't know if any of you have ever, does anybody here remember Dave Fricker? He was an electrical engineer, and he was the board president, and he was just really good. He had all these patents in his name. He comes out to the job site, and he tells us, we're out there putting the pump in, and he's telling us, I'm an engineer and I've got these patents and stuff. And everybody's looking at him, well, I think that's really nice, sir, but we're trying to get this job done or whatever. So at lunch, he goes home and gets the patents, right, and brings it back out to the job site. And he was one of the guys that patented the variable speed, like on a drill, like you pull the trigger harder and it goes faster. And he also had worked at Franklin Electric back when they were developing the submersible motor in the 50s or 40s. Anyway, this Dave Fricker, and you can see he's sitting there next to that wire spool. He's got the Simpson 260 ohm meter there, where he got the leads pulled out. We're ohming it at every joint, right, as we're going in the hole, because we started having problems with these motors. And so these submersible motors, they're very sensitive, and they don't two things they really don't like. They don't like heat because heat burns through the windings and they're shot and that's it. And then unbalanced power. And they had both of those conditions with the water temperature and the unbalanced power. So we put the pump in there. It ran. I think that's the next slide. There's a picture of a label on a high temp motor. We went and we put the pump in the hole, and it ran for like I don't know, 18 months, 2 years, brand new equipment, and then it's running and there's no water at the surface. So we knew we had a hole. We had a hole somewhere. It was in the fluid end. So we went out there to pull that, and we got the elevators on it, and we pulled it up, and it pulled about 2 joints off of it, and the whole thing took off down the hole, the motor and the pump and the 4-aught wire that was tied to it, and went all the way to the bottom. And we went out there. We had to take a drilling rig out there. We fished that out, and we stopped work and said, what are we going to do now? And the engineer decided he wanted to put a string of stainless, 4-inch stainless drop pipe at 850 feet, whatever it was. And so put the stainless in there, and that ran for about 3 years. And then another motor went out. Once again, same thing's killing the temperature, the water temperature, and the unbalanced power. And we got that pump about 2 joints out of there, and it took off. And we pulled it out, and the stainless, you can see it. You see where it cracked? That's the pin. This is the coupling, right? And that's the pin of the jointed pipe screwed in there. And so it was 3 things. It was the strain of the weight of the string. It was the hot water, and it was the chloride in the water that cracked that stainless. And so that's what happened. And it was, and that's what happened when it hit bottom. It bent all that pipe. So we're trying to figure out now, what are we going to do next? And so the decision was made to go with coated pipe, coated 4-inch. So they take a jointed carbon steel pipe, take it to a coater in Odessa, they coat it, and this is the string of that pipe standing in the derrick. You see along with it is the E-line access tube. So we put the coated pipe in there, and it's a real pain to put it together because, and Clark can tell you what a pain it is that the wrenches don't bite on the coating, and you have to have a special set of wrenches to do it, and you always nick it, and anywhere you nick that coating, then it just rusts right through and has another hole. You're back to just carbon steel pipe. So when we stopped going down there, that was the last thing that they were doing was the coated carbon steel. There's another string of it, pulled in doubles. So I'm not sure what in the interim on the starter side, on the electrical side, Mr. Fricker, because he got tired of the unbalanced power, he worked with a company. I don't know if it was Ben Shaw or one of those big electrical companies, and he came up with a current regulator that would take the 3-phase power from the power company, and it would smooth the power, and then it would feed the soft start, and that worked pretty well. In fact, that's what they were using the last time we were down there. But at every turn in this project, it was something big. And I mean, again, you could probably say, well, on the design side, they should have probably done this or that or whatever. But they had never. I mean, why wouldn't you go galvanized? Well, galvanized it'd have a hole in it before you got home, right? I mean, there's no way it would work. And so it was a tough project, and I'm sure they're still fighting it. I don't know if anybody here has any knowledge about that system or how it's going. But again, conclusion there, it's a difficult pumping environment. The maintenance will be ongoing no matter what you put in there. You're going to be pulling it periodically, hopefully not to replace the submersible motor. We did switch to a stainless fluid end, and we stopped the corrosion on the fluid end. That didn't happen again. Knowing that if anything, whenever you're going to have to work down there, you got a long way to town. When you need something, you better have every single thing you think you might need with you. And at least now they have cell phones and Starlink, which then was a one payphone at the motor end. That was it. And I got a little bit of time. This is another project we worked on. This was at Rio Grande Village. This is another Santa Elena well. We got a call. We didn't set the casing on this well. Another contractor did. But when they set their pipe and when they cemented, they lost the packer and they dumped the cement in the open hole section below the base of the surface casing. And for some reason they left, and they asked us what they wanted to do is they came to us and said, we want to underream that Santa Elena. We're just like, well, it's just, I don't see being able to do that. Maybe you guys have done it, but there was no way I could see to do it. And so what we came out with was, and we talked to the chemical company, is we told them we'll go in there and we'll acidize the lower open hole portion. Because it never was a really, y'all were talking about the variability like in the Santa Elena. We saw it here. You saw it at Terlingua how much that well made. That was in Santa Elena. Then this well, when they drilled it and pump tested it initially, it only made 20 gallons a minute. So all the system said was, hey, we'll forget about all this. If you can get us back to 20 gallons a minute, we're going to be happy. And after they dumped the cement, they did the pumping test and it was making about 10. And they said, hey, either you're going to get us 20 or you're going to drill us another well. So we went down. This is us. You can see the Del Carmen's there in the background. This is down by, if you're going around from Rio Grande Village along the river there. I don't know if you all know that territory. I haven't been back since, but that's what I just said. Is that we went in, we put together an acid program. We put the acid away. We took what they said it would take and we basically doubled it. We used sulfamic because it's just a lot safer than trying to do hydrochloric. Also hydrochloric, you can have problems with, or we've had problems using it, cleaning it up and getting the metals back out of it for the water quality for the TCEQ. This is a public supply well. So we used sulfamic, we did it, and then we redeveloped it, and we got it back to 20 or 25 gallons. And so it was a success story, and we didn't have to try to underream that thing. That's just another picture of the location. I think I got one more picture. So this picture is of a drilling rig in Mongolia, and my brother was over there. You worked for USAID, and he sent me this picture when he heard I was doing this talk. He said, you can tell him there is no road to this. When you drive over there, if you want to go over that hill, you just drive over the hill. There's no roads. There's no roads anywhere. And so you can see I guess that's a water tank and probably a Russian built drilling rig. Now those guys, that's remote as much as it gets. And that's it. Any questions or comments or ideas?
Pictures of the observatory.
Well, we drilled 2 wells, and Dr. Stein was involved in that project before we got there. And they had drilled 2 test holes at the McDonald Observatory. And that's all ash and rhyolite layer, interbedded. And it was 8-inch, right? 8-inch pie, 8-inch casing, screened and gravel packed. And we got in there. And started the reaming process. They'd already drilled a test hole, and they had estimated volume, and they'd collected the samples for water quality, and all we had to do, and that always those jobs you hate the worst. All you got to do, right, is rain the hole and run the pipe and gravel pack it and cement. That's all you got to do. So we did. We went in, we did that. Well, what we didn't know is that when they drilled the test hole, they had hollowed out like Carlsbad caverns down there at depth. So we kept stacking air compressors, right, trying to get enough uphole velocity to try to clean the hole. And in the end, it was an interesting resolution because this was going to be the sections that were blown out were not going to be in the screen interval. So we literally went in, we graveled the holes up from the bottom to that level, and we cemented that level, cemented the interval, and then turned around and drilled back through it, and then drilled the gravel out. And we had to do that. One of them we had to do at least twice, maybe 3 times, and that was painful. And we did. We had 3, I don't know, 1,200, 1,500 CFM air compressors tied in together, just trying to, of course, if you've ever done it graveling back and trying to drill out loose gravel, it doesn't go like it sounds, right? I mean, it's really hard to get that gravel back out of there, but it was the only way, or else we were going to cement up the production zone, which we didn't want to do. And, but it was, in the end, we got them, and the volume was good on them. We they met the design rate that the engineer wanted, and so we eventually got out of there. Yes. On
specifically the one you were just talking about, we had the gravel and cement the intervals.
I don't think we logged them. I think they did. Geochem logged the test hole before we got there. No, these are 2 wells, two new wells.
The interesting thing is they were both completed at the same depth, but at completely different water levels.
Yeah, that's right. And their elevation was no difference. Yeah. Yeah, the water levels were different. And
regional maps in that area, they all have nice potentiometric maps that shows
great smooth curves and no elevation difference. Yeah. Yeah, no, it was an interesting project. So anyway, that was McDonald Observatory. Any more questions or ideas?
That's it.
If that'll get me off the stage, yeah.